SHM stands for Simple Harmonic Motion. The definition of simple harmonic motion is repetitive motion that maps out the same path indefinitely for an extended period of time. There are multiple examples of this, right? The majority of which we will be focusing on are springs bouncing back and forth, right? This can be vertically up and down, a repetitive path that continues indefinitely, or horizontal, right? Both of those have different nuances because of the direction of the force, but nevertheless, it's repetitive indefinitely for a long period of time. What we are not addressing is damping. Damping would be the fact that the amplitude in the real world decreases over time. So as it springs up, it gets down, and that A is slightly less, and then the next A is slightly less, and then the next A is slightly less, and after time, you can imagine it just stops vibrating, period, right? So if you were to graph damping, it would look like this and kind of decay over time, right? That's in a real-world situation where you are losing energy to non-conservative sources like heat, right? In a spring, the sheer act of stretching and compressing changes the actual material, which requires energy, which is why in the real world these things do not vibrate indefinitely forever, right? We lose energy to heat. But before we can even start talking about those kinds of things, we need to think about the ideal situation. So in the ideal simple harmonic motion, these things are repetitive with a symmetrical amplitude that continues indefinitely forever. Other examples besides this, today we're going to address moving in a circle, right? If you move in a circle, you are repeating the path indefinitely forever, which is a repetitive motion that can be analyzed through simple harmonic motion. That is the point of this morning's lecture, is to show the analogy or the comparison, or actually the similarities between springs and circles. Because the truth is that the math that governs these things is interchangeable. So if we can discover something using springs, because of the fact that it is simple harmonic motion, we can apply that same concept to moving in a circle. And if we can figure out something having to do with circles that is dependent on repetitive motion over a continuous path, we can work backwards and apply that to springs. This becomes very useful because it's a way of analyzing new and interesting systems that we haven't seen before, but if we can identify them as being repetitive, things that happen continuously over an extended period of time, most likely everything that we come up with through these other systems will apply. And it's extremely useful to be able to transport this knowledge back and forth between the various systems. Later, actually, whenever we have lab, what is that, tomorrow, we're going to talk about another repetitive system called pendulum, right? Pendulum swings back and forth, which is a repetitive system that exists over time, right? And so that also works with everything that we're going to see here, okay? All right, so given this system, the first thing is by adding the mass, right, this dotted line down through the middle here is known as the equilibrium position, right? We could have figured out the spring constant if we'd had the spring by itself, and then by adding the mass, that causes the spring to stretch out to this new equilibrium position. We've already addressed that with Hooke's law, right? F of s equals negative kx. It's a pretty standard calculation, and that's necessary in order to figure out the spring constant. Once we have the spring constant, we know that that elasticity is what's going to drive the repetition of the vibration. The reason why it oscillates is because of the spring, right? We know that at the maximum amplitude, both this position and this position, we are maxed out in terms of energy at a stationary point. Now, this moment happens for just an instant where these things stop moving. But nevertheless, they stop moving, which means the kinetic energy at negative A and positive A is 0, and therefore PE elastic is the only energy term we have at both of those positions, PEE, right? And as a consequence of that would be the maximum potential energy that this system could have. And it would be symmetrical because remember, potential energy is 1/2 kx squared, right? This is why it does not matter if it's negative A or positive A. Squaring the x gives you the same energy term. Right, same energy value. Similarly, yet exactly opposite, is that at the precise moment at the equilibrium position. Since we have added energy to the system and then released it, by doing so, it springs back up towards the equilibrium position. When it gets to this point, it matches the original condition, which means that there is no net force acting on the system because the spring force acting up and the weight force acting down are in balance. They're in equilibrium, which means there is no acceleration, there is no force. At that exact moment, all of the potential energy has now gone away, right? And so now it's moving with a kinetic energy value that is at its maximum. And of course, through the law of conservation of energy, if we were to pick any point in between those two places, right, the spring would be stretched out from the equilibrium position, but it would also be moving. This would happen on the bottom moving up, and also happens on the top moving down. So at this location, somewhere between the equilibrium position and the maximum amplitude, we have both PEE and kinetic energy. Now this is barring non-conservative work due to heat and all of those other things that we review all of that to say that we can use this to derive a couple interesting characteristics that we're going to use later. So at the maximum potential energy, we know that X equals plus or minus A, right, the amplitude. And so the energy max, or the total energy, which really we don't need to say E max, but the energy of the system is fully encompassed in the potential energy, PE elastic, which is the formula 1/2 kx squared, but now x is A. At the equilibrium position, we have a maximum kinetic energy. At the maximum kinetic energy, the velocity is a velocity maximum, right? It is the highest velocity that this system experiences while it's at the equilibrium line, right? In some texts, this is written as V naught, right? But I don't want you to get confused and think that that is initial velocity. That is representing maximum velocity. So I'm going to use the subscript max, but if you read about this in your textbook, it will be V naught. V naught is different than the V naught that we had before, right? So you just have to pay attention to that definition. Nevertheless, E max at the equilibrium position would then be 1/2 mV max squared. So therefore, if E max equals E max, because the total energy of a system is conserved, then these two things can be equal to one another, right? The potential energy at the maximum amplitude can be equal to the kinetic energy at the equilibrium position. So we're just going to set these two equations equal to one another. So mV max squared is equal to Ka squared. And drop the halves because they're common to both sides. We do this because we want to be able to describe the maximum velocity experienced by the system as a function of its physical characteristics. Those physical characteristics are the elasticity, or the spring constant, the mass that is doing the vibrating, which essentially adds inertia to the system, and the amplitude, which is how far it's stretched out, which effectively determines its acceleration. Because the amplitude is analogous to the displacement relates to Hooke's law, which generates the spring force that causes the system to move. All right, so Vmax then would be what? A times the square root of K over M. That's a pretty straightforward analysis, and this is something that you more or less could have done on your own, given a situation where they tell you what the maximum amplitude is. I assume you could have gone through and derived the maximum speed, right? We're going to use that later if I keep moving here. At any point, we know that E max, right, is equal to the total energy. So if I say potential energy, elastic plus kinetic energy at some random point that is not at the amplitude, this could be equal to the Emax at either the equilibrium position or at either maximum displacement, positive A or negative A. In this particular case, we're going to set this equal to the potential energy and do some quick rearranging algebraically. So I know that potential energy at any point would be 1/2 kx squared. I know that kinetic energy would be 1/2 mv squared. And we've already defined the potential energy max as 1/2 ka squared. Obviously, the halves drop out. We're going to do a little bit of algebra and turn it into this. Km a squared times the quantity 1 minus x squared over a squared. Now, we did do a little bit of an algebraic trick there. We divided a out of some terms here, a squared out of some terms here. And since it wasn't common to the x squared, we had to divide by a squared. It's a pretty straightforward calculation. But the reason why we did that is when we take the square root to get v, we get the square root of k over m a squared times the square root of this. And k over m square root times a is the maximum velocity. In other words, the original velocity can be depicted as a function of the maximum velocity. Right? So this becomes v equal to plus or minus a times the square root of k over m times the square root of the quantity 1 minus x squared over a squared. So that means that the velocity of this system can be calculated at any point as a function of its maximum velocity and a square root of its displacement or position at that time compared to its maximum. As I said before, this can be very useful for comparing to other harmonic systems, because in this particular calculation, if we are able to determine the maximum velocity of that system based on its physical characteristics, we can describe the speed at any point based on its maximum displacement and the position it is at that time. More importantly, there is no spring constant or mass in this calculation, which means that going in a circle, which has nothing to do with spring constants, can still be described using this equation, if I am able to figure out how I got the maximum velocity of that system. All right, so right now it doesn't seem to be a comparison, so we have to draw some more pictures to compare this to circles. So we are going to look at a circle. Here's the middle. We're going to do a less detailed diagram and then a more detailed diagram for these two things. Now, the trick with circles is that this is actually a two-dimensional motion in comparison to a spring, which is a one-dimensional motion, right? Spring is up and down or left and right. Circle is up and down and left and right at the exact same time, right? And the reality is to draw the conclusion or the comparison between springs, all we need to do is isolate one direction of the circle and then assume that the other direction is just going to be the inverse of that. So in other words, as I increase in horizontal, I decrease in vertical, right? And so we are looking simply at one dimension, 1D, and in this case, the x direction. So if we're thinking solely as a frame of reference for left and right, call going to the right positive x. If I had a mass attached to, let's say, a string that was spinning in a circle in this direction, right? I can think about it in one dimension as moving back and forth in the x-plane. So as this spins, this mass moves left until it gets to here, and then it moves right until it gets to here, and then it moves left, and then it moves right, and then it moves left, and then it moves right. It does this while also going up and down, right? And so if I were to think about a position like right here at the top, we know that the velocity is now directed this way, right? And it's at 0 in terms of the x position, right? We think of positive x and negative x, which means that this moves from a maximum amplitude in the x direction to a minimum amplitude of 0 back to a negative amplitude to the left, right? And so we've got positive A, negative A, and the equilibrium position, which is the center. So it's exactly the same as what we just saw. This has a maximum potential energy at this point and a minimum potential energy with a maximum kinetic energy at this point. This is based solely on left and right only, right? We're isolating these dimensions. So if I think about here, the reason why this V doesn't apply is because at this exact right position, the velocity is up, which is completely independent of the x motion, and therefore can be described as an x velocity of 0. And so as it gains negative speed, it moves back to the equilibrium position. At this point, it is not displaced from the center, which means it has a maximum value. So this is my V max with my maximum kinetic energy. And then I move over here to my negative amplitude, and I repeat as I go around, right? And so that makes the radius the amplitude. R equals A at this point, and for this vertical line, R equals 0 in the x direction. And all the time, the velocity that is pointed in the x direction is our speed, right? And you can imagine that as we get further this way, because of the fact that the velocity is now directed more and more down, it's directed less and less left, which means it's slowing down as it reaches that negative maximum amplitude at the other side. And so you can see the analogy between the spring and this mass. So we've got kind of the same positions, right? We've got a maximum potential energy here, only it's not PEE, it's just PE, right? And we've got a maximum kinetic energy here. And at any point in between those, we have both, right? And that's what we're going to use the second circle to depict. If I were to draw out this mass at some position between those maximum points, the radius is still the amplitude, right? But now, if we're thinking about it in terms of the x direction only, right, then I have to drop a vertical, and the displacement is the horizontal component of that triangle. This is x. Oops. Furthermore, the velocity, which is tangent to the path, is always V max, regardless of what direction it's pointed in. It's just not always pointed in the x direction. So this is still V max as a numeric value. It's just that the ball is not experiencing that in the x direction at this point, right? But thanks to vector resolution, we can derive triangle.
Okay, now there's just arrows every single direction.
There's 3. This one measures the horizontal component of this triangle, right? Because remember, we're talking about the x-plane only. So what I'm doing is picking a position that is not centered on exactly to the right or exactly vertical, and then resolving into horizontal and vertical components, right? The horizontal component of the position is x, right? So on this number line, left to right, this is this far away from the equilibrium position. And as it moves towards the top, it will be back to 0, and then it will go negative, and then it will come back and go back and forth and back and forth. The velocity does the same thing. As this rotates it points more and more left until it reaches to the top where the entire velocity points left, right? But at this point, it's not the entire velocity, it's just this piece right there, v. But the geometry is that this angle, theta, is similar in triangle to the top angle in this triangle. I apologize, I'm running out of room, but this is theta right there. So I have two triangles, one based on position and one based on speed, both of which are similar based on theta. So I can say that the sine of theta in these two triangles is equal to the opposite over the hypotenuse, which is the velocity divided by the maximum velocity, and the opposite divided by the hypotenuse, which is the square root of a squared minus x squared divided by a squared. No, excuse me, a. So we,
Square root over everything in the top?
yes. Remember that this is a right triangle, right? A squared plus b squared equals c squared, right? So this side is the square root of a squared minus x squared. That's from Pythagorean theorem. It is just a. That's the hypotenuse of this triangle. So I show you that because this, right, says v equals v max times the square root of 1 minus x squared over a squared. What we just proved is that the speed is dependent on the maximum speed and its position based on its maximum displacement, which is what we just did a moment ago in springs, and we got the exact same equation. So this is evidence that these things can be ported from one system to another as long as it's repetitive in a simple harmonic way. Repeats the same path without decay for an extended period of time. Right? So you can double check that, but that's the exact same equation that you just wrote down a moment ago. So why do we do that? Well, because we can learn other information from the circles, and then without having to go through another grueling proof, we can assume that whatever we can take from the circles can then be applied to the spring system, right? These things are interchangeable is the whole idea. So if I think about the circle, right, we can describe it as a function of period. Period is the time it takes to vibrate through one complete cycle. So in this case, going all the way around the circle back to the original position. If we think about it in terms of x, that means from moving from the maximum amplitude to the maximum speed to the negative amplitude to the maximum speed back to the original position. One complete cycle, right? But we also know that the maximum velocity for circles is just circumference divided by period. Except that now we've defined the circumference as 2 pi times the amplitude. This is valuable because it allows us to put the period in terms of the physical dimensions, 2 pi a, and the speed, v max. We're going to pause there and think back to what we just did on the other page. Recall that v max for the spring system was the amplitude times the square root k over m. So the amplitude divided by v max is equal to the square root of m over k. Now careful, I flipped that around because it's not v divided by a, it's a divided by v. Right? We inversed underneath the radical because we switched the sides that we're dividing. We did this because a divided by v is in our period calculation. So we can substitute this information in where a over v max is. Since the maximum velocity is a function of the physical characteristics, combining A over V max as the root of m over k allows us to describe the period as 2 pi times the radical m over k. This is valuable and also interesting because there is no k in circles. The whole point of this, right, is that we put the period of the circular motion as a function of its physical characteristics and its speed. We then took the information that we know from the springs based on its speed and reintroduced the mass and the spring constant, which means that this period formula, which came from circles, can now be applied to a spring system. But more importantly is the fact that the amplitude and the maximum speed drop out. This is very, very intriguing because of the fact that a mass hung on a spring will vibrate the exact same no matter how far I stretch it out before I let go. The maximum amplitude is independent of the system. It's independent of amplitude and maximum speed. This is remarkable because in terms of simple harmonic motion, that means that a vibrating system will vibrate with the same frequency and period regardless of how far away the system has been displaced at the initial conditions. This is what you're going to explore in the pendulum lab tomorrow. But this is extremely useful for a variety of systems, right? The amplitude is independent of the overall vibrational characteristics. Does that make sense? This is something that we see in a variety of different simple harmonic oscillators. One of the most prevalent is light, right? Light is an electromagnetic wave that vibrates through a particular amplitude carrying a frequency and wavelength. The amplitude, which effectively is the brightness, right? The intensity of the light does not change the color of the light, which to us is a very intuitive system, right? Red is red no matter how bright it is. But the reason why is because the system is independent of the amplitude. And that's extremely important, right? How the maximum energy contained by the system does not determine how that system vibrates. That's a very unique characteristic. So let me show you an example from your homework in the last minutes here. There was a homework problem on the simple energy assignment that gave you a spring like this. They then said if I add a mass to it, it stretches out some distance. In mine it was 0.3 meters or 30 centimeters. And then there was a and then discussion where we took this at this now defined equilibrium position, right? It's not the equilibrium position of the spring itself, it's the equilibrium position of the spring and the mass, right? This is the beginning of the first picture I started with. So we use this to find K, but then we're going to stretch it out another 10 centimeters, 0.1 meters, and then let it go. So it starts out, apologize for the crappy spring, it starts out at negative A, right, at a maximum amplitude, and then is released. And the question is, how long does it take to return to the equilibrium position? So in other words, if I stretch this out 10 centimeters below the equilibrium position and I let go, how long does it take to get back to here? The reason why this is a complicated question, if you remember when we did the Hooke's Law lab, the acceleration is non-constant, right? As this gets closer to the equilibrium position, the force decreases, which means that all of your classical kinematics, right, everything that we've done with your acceleration equations doesn't work, right? You cannot calculate the time because the acceleration is changing over time. But if we think about this as a system that is vibrating through a period that is going to repeat over a time frame, if we can figure out what the period is, then we know the time, right? And all we have to do is break it down as to what portion of that time it is. So this was 2 steps, right? First was finding the spring constant, because that's necessary in that period formula. So if we use Hooke's law, f of s equal to negative kx, we know that the mass hanging down generates a weight at this equilibrium position. The spring force acting up and the weight force acting down are in balance, which means that mass times gravity, or weight, is equal to k times x in terms of magnitude. And you can go through your Newton's second law summation of the forces calculation to really see that. But nevertheless, mass times gravity divided by x. I think my mass was given as 1.5 kilograms in this example. So 1.5 times 9.8 divided by 0.3 gives me a spring constant of 49 newtons per meter. Once I have the spring constant, then I can simply plug into the period formula. T equals 2 pi times the square root of m divided by k. As I said, n was given as 1.5, and we just figured out k is 49. So you plug those things in, and you get 1.1 seconds. The problem with that is that that defines the time for one complete cycle, right? And going from here back to the equilibrium position is not a complete cycle, right? And so it's best to really look at it and think about it as waves, right? If this is the equilibrium position, I started here, I go back to the equilibrium position, I go to the maximum value, back down to the equilibrium position, sorry, and then back down to where I started. This is a complete wavelength, which is one complete cycle, right? So it's analogous to waves. If you think about it similarly, not in this problem, but it helps to visualize the waves. If I started at the maximum speed, then I would start at the equilibrium position. I would move to the maximum amplitude, go back to the equilibrium position, go down to the minimum amplitude, and then go back to the equilibrium position. This is a complete wavelength, right? It's a complete cycle. Now the thing is that that's in 4 pieces, right? Moving from one position to the equilibrium, moving from the equilibrium back down, and then back down, right? And so to go back to the question, to move from here to the equilibrium position is simply 1/4 of an overall cycle, because there's 4 sections, right? And so the time it takes to return to the equilibrium position is the period divided by 4. T equals period divided by 4, which in this case is 1.1 divided by 4, which is 0.27 seconds. The idea being, I don't need the equations of motion. I, in fact, can't use them because the acceleration is not constant. But I can think of it as being a wave, or being something spinning in a circle returning to its equilibrium position, right? It's a repetitive motion that maps out a period that works just like any of the other wave functions.
Is it always going to be period divided by 4?
Well, so it...
For like this scenario?
That's only for this scenario, but that's only because we're going from the maximum A, right, here, negative A, back to the equilibrium position.
Mm-hmm.
If the question was, for example, how long does it take to go from here to its maximum height, right, then that's half the problem.
Okay.
Does that make sense?
Yeah.
And there would be, the similar question would be, and probably a more straightforward one, is how long does it take for it to return to its original condition, which is just the period.
Yeah.
Does that make sense?
Yes.
Because the same thing could be true, is the question could be something like, how many times does it oscillate in 30 seconds? So then you have to figure out what the period is, take 30 seconds and divide, right? All different ways of basically asking the exact same information. But the idea is that the time for this system can be described without having to use an acceleration because of the fact that we used energy to compare. Make sense? The cool thing we're going to talk about a little bit later is that some systems that don't have spring constants will still follow this same kind of pattern, where we can represent elasticity in a different way. Even though it's not elasticity, it's still a restoring characteristic. That's what you're going to look at in the lab.